Welcome to the chapter on the filtration function of geosynthetics. The filtration function is closely associated with the separation function, but concentrates on the flow of liquid through the geotextile and its interface with the soil. It is defined as restraining of uncontrolled passage of soil or other particles subjected to hydrodynamic forces while allowing the passage of fluids into or across a geosynthetic material. Again, filters are needed to allow free flow of water and to restrain uncontrolled fine particles from passing through. Engineers have used stone filters to speed up the flow to create a controlled flushing effect for the particles which are moving through the soil. Sometimes it doesn't work, especially in slow-flowing applications, such as the extreme example of the base of a landfill, which has a relatively flat floor covered in 40mm drainage stone, now clogged with silty organic particles. It could be a French drain, which has a slow fall where the soil and silt accumulate in the stone and even, in the end, clogs the pipe. The solution is a geotextile filter separator, which can be easily laid around the trench, in the case of the French drain, before placing the stone. The edges can be flapped over, completely wrapping the stone. This gives a large surface area for the water to flow through and keeps the stone relatively clean. But does the geotextile clog? The answer is yes, they can, but only in very extreme circumstances. Geotextile filters have a very high degree of redundancy in that the permeability of the geotextile is usually over 100 times more permeable than the soil being filtered. Even if the geotextile was 80% clogged, there would be no notable change in its ability to function. As the geotextile is so thin, it will tend to flush with any hydraulic buildup. Maybe a diagram will help us understand what is happening at a particle level. Geotextile filters can be carefully designed based on their opening size, defined by testing, and can be matched to any soil which encourages what is known as a Terzaghi filter to build up at the interface. Let's look at how this works. In the diagram, a filter geotextile, in this instance, is attached to a drainage geocomposite core, leaving free space for the water to drain. The soil is separated by the geotextile, preventing it filling the void in the composite. As water flows from a low energy environment due to the low permeability of the soil to a high energy environment in the void, the higher energy starts to move small particles of the soil, and some of the particles are designed to migrate through the geotextile, followed by a few medium-sized particles. Coarse particles cannot pass. This continues for a short time until a stable state occurs, where in an area about 150 millimeters from the interface, the particles filter each other back into the soil and there is little or no more particle movement. This is known as a Terzaghi filter. Water will then continue to flow over the lifetime of the drain in this stable state. Typically, a geotextile used in the UK will have an opening size around between 70 and 100 microns, that's 0.1 millimeters, which is the range of the silt fraction of an average soil in the UK. We have seen a very common use of geotextiles in a French drain. Another major application is under rock armour revetment. Typically, Rock armour is used where embankments to rivers and coastal areas are subject to wind-blown waves or heavy flows which, if untreated, will erode away. Fine sands are particularly erodible, so weighting it down with heavy rocks which also break up the waves is a good solution in sensitive areas. The problem is the gaps between the rocks, and when the waves or flow of water occurs, the subsoil is sucked through the gaps between the rocks. One answer is to use a similar idea to the Terzaghi filter, where progressively bigger stones in a series of layers are placed in succession to prevent the layers below migrating out to the surface. Well, this works in theory, but it is very expensive and in some instances virtually impossible to construct, especially below water. The solution, of course, is to place a robust geotextile filter separator onto the subsoil and overlay this with just 1 or 2 layers of rock, dependent on the attack level. These geotextiles are overlapped and the rocks will then hold them in place. There are roller devices which can be used to deploy the geotextile underwater as shown. This method allows installations from barges where proper control is achieved, where previously it would be nearly impossible, say at the base of a sea cliff, for instance. The savings in time, material costs and environmental savings are considerable. There are many examples around the UK coast. Let's look at the London Gateway on the Thames estuary. London needed a large container port which could take the ever-growing size of container vessels travelling the globe. A site near Canvey Island on the Thames estuary was chosen, and an area of dredged sand was developed out into the estuary to reach into the deep water channel. This exposed site was subject to large waves and the bow thrusters from the visiting ships. If left, the dredged sand would quickly disappear. The sloping leading edge was to be covered in a 1-ton primary rock overlaying a 300-kilogram secondary rock to prevent erosion. The sand was shaped into a long, shallow sloping embankment, and a filter geotextile was rolled out from the toe below water and then up to the crest. This is followed immediately with placement of 2 layers of rock. You can see how the geotextile lays in close contact with the sand, preventing its movement but allowing free flow of water in and out of the embankment, especially when wave attack occurs. The embankment is now protected and the container port open. It recently celebrated with the world's largest container steamed into the port and docked successfully. The geotextile filter in the last example had to be open enough to allow high permeability caused by wave attack without loss of relatively large sand particles. In this instance at Wallasey Dock near Liverpool, silt had built up over many years and virtually filled the dock, making it no longer usable as a dock and a safety hazard for anyone who might fall in. The port no longer needed the dock, but the problem was the disposal of the silt, much of which was contaminated from industrial use in the past. The problem is how to dredge out the contaminated silt, and where do you put it when you have? The solution was to supply a series of high-strength sheets of fine filter geotextile, which are then sewn together into one giant piece. The sheet is then pulled across the dock, floating on the surface water. Fill is then placed around the perimeter of to act as an anchor. Note the water coming up through the filter as the first bucket load is placed. Then the dredged sand fill material, which has a much higher permeability than the silt, is dozed onto the surface. This surcharges the saturated silt, and the water passes through the filter and overflows the dock and is safely collected and treated. The whole surface is covered and then extra surcharge placed on top to accelerate consolidation. Eventually, the silt is dewatered. The settlement is complete, leaving a hard standing for container lorries. This fine filtration method leaves a clean, firm, reusable site with massive savings over removal or treatment of the silt. We have looked at filtering average soils in the UK to prevent clogging of stone filter drains. Also high flow reversing filters in rock armour revetments applications, and then closing of silt or sludge lagoons with tight filters holding back the silt fraction whilst forcing the silt to dewater. Some of the other applications which may interest you are mentioned above. Further guidance on the design and execution of geosynthetic filter solutions is as shown in the list above. Another great source of information on all geosynthetic applications is to be found by joining the UK chapter of the International Geosynthetic Society with a dynamic student membership, which is also free for students in the UK. Joining also gains you access to leading geotechnical journals and conference proceedings, and even the chance to put papers and academic research into upcoming geotextile conferences around the world.